So I will discuss about the ringdown of compact objects other than black holes. And essentially, we will see how we can test the nature of the astrophysical sources by looking at the ringdown stage of a gravitational wave signal. And we will see in the case in which the remnant of coalescences is a horizonless alternative to black hole, how the ringdown will change in the quasi-normal mode spectrum in the emission of gravitational wave echoes. And we will do some preliminary analysis to assess the detectability of these extra signatures. So essentially, as we have seen during this conference, so far we have detected 90 gravitational wave events from the coalescence of compact binaries. And in this talk, I will focus specifically on the ringdown stage, in which the final remnant of a coalescence relaxates to an equilibrium solution. And the main question I would like to address is what is the nature of the remnants of the events we observed so far. And indeed, from the detection of the ringdown, it is possible to infer the nature of the remnant by looking at the quasi-normal modes of the system. Essentially, the ringdown stage is dominated by the characteristic frequencies of the remnant, the so-called quasi-normal modes, and they are complex frequencies. They describe how the remnant respond to a gravitational perturbation. And the ringdown signal can be modeled as a sum of exponentially damped sinusoids, where the frequencies are related to the real part of the quasi-normal modes of the remnant, and the damping times are inversely proportional to the imaginary part of the quasi-normal modes of the remnant. So from a detection of the ringdown, we can infer the characteristic frequencies of the remnant and understand its nature. So far, we have detected the fundamental quasi-normal mode in several gravitational wave events, and these observations are compatible with Kerr black holes as predicted by general relativity. However, if we would like to perform a test of the no-hair theorem, we will need to detect at least two quasi-normal modes. In this way, we could check if the remnant has extra degrees of freedom, or if it is just described by a mass and the spin as predicted by general relativity. And indeed, in the future, with next observations, and especially with next generation detectors, we will be able to distinguish between several models. And from a theoretical standpoint, there are several models of alternatives to black holes that are as compact as black holes, but they do not have an horizon and they do not have a curvature singularity. So these models come from some quantum gravity extensions of general relativity, or are conceived within general relativity, but with some dark matter or exotic fields. And among all the models, we can recall fuzzballs that come from string theory, or boson stars with some ultralight dark matter fields. And some of these models can mimic black holes in terms of electromagnetic observations, but they will have some characteristic smoking guns in the gravitational wave signals. I will not focus during this presentation on some specific models, but we will analyze all of these class of models as a tool that allow us to understand if the remnants of compact binary coalescences have an horizon or not. So essentially, we can classify all of these models depending on two parameters. And so they deviate from the black hole solution for their compactness and their darkness. And in this sense, this is why we can call them dark compact objects. So related to the compactness, these models have a radius, which has an epsilon distance with respect to the would-be horizon of a black hole. And in this sense, we can have objects with different compactnesses. Some of them are ultra compact, so very similar to black holes, whereas some other ones can have compactness with a radius near to the light ring of black holes. And then these solutions have different reflective properties depending on their interior solution and their degree of absorption. So we can distinguish dark compact objects from black holes by looking at their quasi-normal modes in the Ringdown. So we will perturb the compact object with a gravitational perturbation. And the perturbation is governed by a second order differential equation and is subjected to an effective potential. And here we can see what is the main difference with respect to the black hole case. So in the black hole case, the effective potential that is subject to the perturbation has a peak at the light ring of the black hole, and then is such that the perturbation is purely ingoing towards the horizon of the black hole. In the case in which the object has a radius, then there is a cavity between the radius of the object and the light ring that will determine a completely different quasi-normal mode spectrum. So what we are going to do is to derive the quasi-normal mode spectrum in the case of dark compact objects. So this is an eigenvalue problem. So we need to add two boundary conditions to our second order differential equation. And the most important part here is to derive a proper boundary condition that describes a generic compact object with a given radius and a given reflectivity. So in order to derive this boundary condition, we generalize the membrane paradigm to dark compact objects. So the membrane paradigm was originally developed for the case of black holes, and is such that an observer outside a perturbed black hole can replace the interior of a black hole by a fictitious membrane located at the horizon. And the junction conditions are such that the fictitious membrane is a viscous fluid with some bulk and shear viscosities. So essentially, we can map the interior of a black hole in terms of so we made use of this paradigm and generalized it to describe generic dark compact objects with a sparse exterior, but with different interior solutions in terms of the properties of a fictitious membrane. And by imposing this boundary condition, we derived the quasi-normal mode spectrum of dark compact objects. So here we see the real and the imaginary part of the quasi-normal modes as function of the radius of the object that is changing. So we see that when the radius of the object coincides with the horizon, we recover the quasi-normal modes of the black hole case, but when the radius of the object increases, there are deviations from the black hole quasi-normal modes. So a first important feature that we observe is that axial and polar modes are not isospectral, differently from what happens in the black hole case. And then we also see that these deviations would be compatible with current measurement accuracies associated to the quasi-normal modes. Here, these accuracies are highlighted in red, and we can see that essentially modified solutions with epsilon smaller than 0.1 would be compatible with current measurement accuracies. And if we look at the Ringdown signal in time domain, this is how it will change in the case in which the remnant is horizonless. So in the case in which the remnant is ultra compact, we will see the same prompt ring down of a black hole, since this is due to the excitation of the light ring. And then there will be the extra emission of gravitational wave echoes due to trapped modes in the cavity that leak out through the potential barrier. Here, the time delay between echoes depends on the width of the cavity, and the amplitude of the echoes depends on the reflective properties of the object. Whereas in the case in which the radius of the object is near to the light ring, we can have also modifications in the prompt ring down, due to the fact that the first gravitational wave echo would appear earlier and would interfere with the prompt ring down. So far, we haven't detected any gravitational wave echo in the LIGO Virgo data of 3B, and we can put constraints on modified solutions. In particular, we can constrain the compactness of the remnants, and from current observations, it has to be larger than 90% one of a black hole. In particular, here in this plot, we can see how the real and the imaginary part of the quasi-normal modes change when we vary the compactness of the object on the x-axis and the reflectivity of the object on the y-axis. And the dashed regions are the regions of the parameter space that are already excluded by current observations. But in particular, with next generation detectors, we will have a signal to noise ratio in the ring down that will be of an order of magnitude larger, and would allow us to actually say something more about the remnants of coalescences. And in particular, next generation detectors would be able to probe values of the reflectivity that are close to the black hole case. So they would allow us to probe more the nature of compact objects. I just would like to mention before the conclusions that recently we have also generalized the membrane paradigm to the case in which there are some quantum fluctuations at the horizon, described as a Gaussian wave packet with some amplitude and some standard deviation. And in this case, the object with some semi-classical quantum modifications can produce gravitational wave echoes, as shown in this plot here. However, the amplitude of the echoes will be small, and it probably will not by our detectors. So I will draw my conclusion that with gravitational waves, we can infer the nature of compact objects, particularly looking at the ring down, by looking at some modifications in the quasi-normal modes with respect to the black hole case, or in some extra signal known as gravitational wave echoes. And for sure, in the near future, we could perform tests of the nature of the black hole paradigm. Thank you.